Hello everyone, my name is Bayode Owolabi, and today I'll be giving a talk on my computational work on turbulent flows in ducts. So the title of my presentation is Marginally Turbulent Couette Flow in a Spanwise Confined Passage of Square Cross-Section. Before I continue with the talk, I will first define some of the terms in the title. So first, we have marginally turbulent flow. And by marginally turbulent flow, we are referring to flows at Reynolds numbers just above transition. And as I will show you later on, at these Reynolds numbers, interesting things happen. So next, we have Couette flow. Couette flow refers to a flow which is driven by moving wall. So you don't have a pressure drop. You don't have a pressure gradient. This work was carried out in collaboration with Professor Chao and Lin from National Tsinghua University in Taiwan. First, I will give a brief background to the study. And let us consider turbulent flow through a pipe. If we plot the contours of the mainstream-wise velocity, you get the figure shown on the slide. As you can see, the profile is axisymmetric. Again, if you look at the cross-stream velocity components, when they average in time, they vanish. So in this case, you do not have secondary motions. Again, if you compute the shear stress at the wall, we will discover that the distribution of the shear stress along the circumference of the pipe is uniform. So this is the situation when you have a pipe. But what happens when you remove the span-wise homogeneity? When you do that, there's a distortion in the velocity profile, and that is what you get in non-circular ducts. For example, in a straight square duct, you have the mainstream-wise velocity contours bulging towards the corners of the ducts. And if you look at the average flow field in the cross-section of the ducts, you see secondary motions appearing. You can get these secondary motions in non-circular ducts. For example, in the triangular ducts, you have the secondary flow shown on the slide. This secondary flow is referred to as Prandtl secondary flow of the second kind, and it is generated by gradients of Reynolds stresses. So they do not exist in laminar flow, because in laminar flow, there is no Reynolds stress. So in this talk, the focus will be on turbulent flow in ducts, in a square duct, because the square duct is perhaps the simplest flow exhibiting the Prandtl secondary motion of the second kind. So this makes it an ideal geometry to study the fundamental structure of turbulent flows when you have a main three-dimensional velocity distribution. So in the literature, most studies have been focused on the square duct. But before we continue, let us take a step back and consider the pressure-driven flow in a square duct. Experimental studies have been carried out at relatively large Reynolds numbers. So we have shear Reynolds number greater than 4,000. And let me define the shear Reynolds number. It is defined in terms of the friction velocity U tau, the half height of the duct, and kinematic viscosity, where U tau is the wall shear stress divided by the density. At these high Reynolds numbers in the square ducts, the experiments have found that the flow is characterized by secondary motions. The secondary flow consists of 8 vortices, and these vortices transport momentum from the center of the duct to the corners of the duct and back to the center. Although the secondary flow is very small in magnitude, it is less than 2% of the primary flow, it has a significant influence on the momentum and heat transport. Again, if you look at the contours of the mean streamwise velocity, which is on the right-hand side and on the slide, you see that the contours bulge towards the corners of the duct because of the secondary motions. And with development in computational fluid dynamics, it's now possible to carry out direct numerical simulations of these flows. However, due to computational restrictions, DNS is limited to relatively low Reynolds numbers. But at these Reynolds numbers, the DNS has shown that the flow structure is very different from what is observed at relatively large Reynolds numbers. And one example of a direct numerical simulation carried out at a Reynolds number close to transition is the DNS of Ullmann et al. And here they show that at the marginally turbulent Reynolds numbers, the flow is characterized by 4 secondary flow vortices rather than 8 vortices. And these vortices keep changing their orientation in time. So what they've done is that they've averaged the flow field over short time periods, and at some averaging period, they get the secondary flow pattern shown on the left-hand side, and then at some other period, they get a secondary flow pattern shown on the right-hand side. So the flow keeps alternating between these two configurations. This switching of the flow field, when it happens, if you average the flow over a long time interval, you get back the 8 vortex secondary flow pattern. So the 8 vortex secondary flow pattern is a composite of the 2 4 vortex secondary flow pattern. And the switching of the flow field has been verified experimentally. So in our previous studies, we monitored the velocity at some certain distances from in the duct, at certain locations in the ducts, and we were able to compute the probability density function of the streamwise velocity. We observed that the PDF was bimodal. This shows that the flow switches between 2 states. So we've been able to verify this alternation in states experimentally. So there's this question that we need to answer, and that question is why the flow field is switching between 2 states at relatively low Reynolds numbers. To answer this question, we need to look into the coherence structures, which are the building blocks of the turbulence. The common coherence structures are the quasi-streamwise vortices, shown on your left-hand side, and the high and low speed streaks. In a turbulent flow, fully turbulent flow, you have several of these structures hosted within the ducts. The average separation distance between the velocity streaks is about 100 in wall units. So what happens when you introduce sidewalls into the flow is that the number of these structures that can be hosted within the span of the ducts becomes limited. So in the marginally turbulent case, the width of the duct in wall units is just barely large enough to host the coherent structures needed to maintain a self-sustained turbulent flow. So what happens is that at any given time interval, at any given time, turbulence activity is concentrated on only 2 walls, while the remaining 2 remain quiescent. If you look at slice from simulations, which I will show you later on. You can see that you have just two high-speed streaks hosted within the ducts. And these are very small. The number is very small, so the flow field has to alternate between two states in order to maintain turbulence. We still have some unanswered questions though. So the first question is whether or not this switching between two states discovered in the marginally turbulent regime is unique to pressure-driven flows. So we want to know whether you also get a switch in states in wall-driven flows. And to determine this, first, we need to work out the critical Reynolds number for obtaining a turbulent flow in wall-driven flow. And after finding out the critical Reynolds number, then we can investigate the flow field at Reynolds numbers close to transition. This next part of my talk will be focused on the turbulent flow in square duct, which is driven by wall motion. And we'll be carrying out direct numerical simulations at low Reynolds numbers. The geometry we are considering is square ducts, like I've said earlier on. And here we have motion of the wall, both at the top and at the bottom. And the wall is moving, the two walls are moving at the same speed, but in opposite directions. And this results in a zero net transport of fluid through the ducts. Before I continue, let me introduce another Reynolds number, which is based on the velocity of the wall. The governing equations we are solving are the continuity and momentum equations. And here we've set the pressure drop, the pressure gradient to be zero. We employ the no-slip boundary conditions at the walls, and we enforce periodicity in the streamwise direction. So what comes out of the ducts is fed back into the ducts. For the direct numerical simulations, we make use of the finite volume method. The finite volume code has a second order accuracy in space and time. The equations are advanced in time using a semi-implicit fractional step method. And in this fractional step method, the convection terms are integrated in time using the Adams-Bashforth scheme, while the diffusion terms are integrated in time using the Cranston-Gaussian schemes. And spatial derivatives are evaluated using second-order central difference schemes. Our grids, the grids that we use are symmetrically clustered grids. Close to the walls, the grid size is very small, but as you move away from the wall, the grid gets bigger. But if we consider the wall bisector, close to the wall, we have the grid size to be about 0.04 in wall units. But then when you get to the center of the duct, the grid size is about 4.05 in wall units. In the streamwise direction, we make use of uniformly spaced grids with a distance with a size less than 9 in wall units. And to maintain stability in our simulation, we ensure that the CFL number was less than 0.3. Now I will take you through the results of investigations to determine the critical conditions for obtaining turbulent flow in wall-driven square duct flow. We know that the transition from laminar to turbulent state is subcritical in the ducts. So this is very sensitive to inertial conditions. In theory, you can have laminar flow indefinitely. Well, as soon as you introduce disturbances into the flow, then the flow becomes turbulent. And the Reynolds number at which you obtain a turbulent flow is dependent on the amplitude of the disturbance introduced into the flow. And there are different approaches to study laminar turbulence transition. One approach is to start from a laminar base flow and then introduce a disturbance into the flow and observe the Reynolds number at which the flow becomes turbulent. Another approach is to start from a fully turbulent flow field and then gradually vary the flow parameters, such as the Reynolds number and the length of the duct, until the flow relaminarizes. In this study, we made use of the second approach, that is, we started from a fully turbulent flow. And we have a map showing the laminar and turbulent states. The turbulent states are represented by the on-field symbols, while the laminar states is shown by the field symbols. The dotted line indicates the laminar turbulent boundary. Here in this plot, I've shown the length of the ducts on the vertical axis and the Reynolds number on the horizontal axis. One thing that we can observe from this plot is that the critical Reynolds number for turbulent flow is 875. So below a Reynolds number of 875, you cannot get turbulent flow. You can only get laminar flow. Again, what we've done to obtain this plot is that we start from a fully turbulent flow field, and then we gradually reduce the length of the ducts until the flow becomes laminar, or we reduce the Reynolds number until we get a laminar flow. The critical Reynolds number for obtaining a turbulent flow field is much higher than what you get in plain Couette flow. We think this is because of the stabilizing effects of the side walls on the flow. And we were able to verify that that is indeed the case. We carried out some simulations on ducts having aspect ratios of 2:1 and 4:1, and we observed a decrease in the critical Reynolds number. So we can say that the side walls in the square ducts have a stabilizing effect on the flow. Having determined the critical Reynolds number for getting a turbulent flow field, now let us examine the turbulent flow field at Reynolds numbers not too far from transition. So here, the Reynolds number we are considering is 1,500. The figure on your slide shows the velocity field. The contours are the contours of mean streamwise velocity, and the vectors are the secondary flow vectors. We observe that when you average over short time intervals, in some time intervals you get the flow field shown on your screen, and then in some other time intervals you get the average flow field shown on your screen. So the flow is switching between these two configurations. So the second configuration is the mirror reflection of the first configuration. Therefore, we have been able to show for the first time that this switching in the flow field between two states is not unique to pressure-driven flows alone. You also get it in wall-driven flows. So when you average the flow field over a long time period, you get a secondary flow pattern characterized by four vortices, which are symmetrical about the vertical and horizontal bisector. And now we have to come up with a way of identifying the states. If we look closely at the central portion of the ducts, you can observe that in one state, the secondary flow is pointing mainly downwards, while in this other state, the secondary flow is pointing mainly upwards. So if we can work out the magnitude of the secondary flow in the central portion of the duct and assign a sign to that value depending on the direction in which the secondary flow is pointed. We can also define an indicator function as shown on the slide. The indicator function varies from -1 to +1. When the flow is in the states on the left-hand side, you have the negative value of the indicator function, and when the flow is on the other states, shown on the right-hand side, you have a positive value of the indicator function. And if we look at the evolution of the indicator function with time, we see the pattern shown on your slide. So clearly we can see the switching of the flow between these two states. And if we look closely, we observe that the time spent in each state is of the order of 1,000 time units. So having confirmed the switching of the flow between two states, now we are interested in finding out the origin of the secondary motion. To do this, we can take a look at the equation of the mean streamwise velocity. And this equation has different terms. So the C term represents the convection of streamwise velocity by the secondary flow itself. The D term is the diffusion of streamwise velocity by viscosity, while P1 and P2 represent the contribution of the Reynolds shear stress and the Reynolds normal stress to the production of velocity or to the dissipation of velocity. So the Reynolds stress terms can either be a production term or a dissipation term. Now we can investigate the budget of the mean streamwise velocity. We consider a line passing through the center of the corner vortex as shown on a slide. And we work out the contributions of the different terms in the mean streamwise velocity equation. You can see that close to the wall, the normal stress term is responsible for production of streamwise velocity. So the gradients in the Reynolds normal stresses are responsible for this corner velocity. Again, if we consider a line passing through the center of the large vortex, and we look at the budget of the terms in the velocity equation, we can see that the shear stress term is what is contributing to the production of streamwise velocity. So the gradient in the Reynolds shear stress is crucial to the formation of the large vortices. Now, let us consider some turbulent statistics. Here I've shown the profile of the mean streamwise velocity, and the profile has been computed along the moving wall bisector. So the solid dark line represents the profile at the lower portion of the duct, while the red dashed line is the profile at the upper portion of the duct. And I've included the plain Couette flow data of Asakisov for comparison. It can be observed that at the lower portion of the duct, the velocity profile follows the log law, while at the top part of the duct, you have an overshoot from the log law. We can explain this difference in the velocity profile by working out the wall shear stress at the wall, at the upper and lower wall. So at the lower wall, the shear stress is higher than at the upper wall. And if you work out the Reynolds number based on this shear stress, it is higher at the lower wall than at the top wall. So the flow at the lower wall is more turbulent than what you have at the upper wall. And that explains why the more turbulent flow agrees with the log law, while the less turbulent flow has an overshoot from the log law. So this overshoot is a low Reynolds number effect. And the long-term average flow data lies between these two profiles. Again, here we have the profiles of the turbulence fluctuations. And again, the dark line shows the profile at the bottom half of the duct, while the red dashed line is the profile at the top half of the duct. The long-term average data is what is shown as the dashed dotted line. And if you look closely at the plot, you see that the fluctuations in the long-term average data is higher than what you get in the short-term average data. So why is this so? This is because at some instance in time, the flow is fluctuating about a mean which is larger than the long-term average. And at some other instance in time, the flow is fluctuating about the mean which is lower than the long-term average. So in the long run, the fluctuations about the long-term mean becomes large. And that's why you have a higher fluctuation in long-term average data. Again, if you look at the plot of the streamwise velocity fluctuation close to the lower wall, you see that the peak in the URMS plot is closer to the wall at the bottom half of the duct, but at the top half of the duct, the peak is further away from the wall. So we can explain this again based on the fact that the Reynolds number, the local Reynolds number at the lower wall is higher than what you have at the upper wall. So in the literature, when you have a higher Reynolds number, the peak in the streamwise velocity fluctuations move closer to the wall, while at lower Reynolds numbers, the peaks move away from the wall. So this agrees well with the literature. In this plot, I've also shown the wall normal velocity fluctuations and the plane Couette flow data of Asakisov is also included for comparison. Having looked at the turbulent statistics, let us now consider the Reynolds stress tensor in detail and compute the anisotropy invariance map. The Reynolds stress tensor has invariance, and if we work out the second invariant and the third invariant, they should always lie within this triangle known as the Lumley triangle. So depending on where the data point lies in this triangle, the turbulent flow structure is different. So on this line on the right hand side, you have a rod-like structure. On the left-hand side, you have a disc-like structure, while at the top, you have the two-component structure. So at the lower vertex, you have isotropic turbulence. On the vertex to the left-hand side, you have two-component axis-symmetric turbulence, while on the top vertex, you have one-component turbulence. For our flow, we're able to work out the invariant of the Reynolds stress tensor. So we have the data shown on the slide. I've also shown the data of Asakisov for plane Couette flow. We can see that the flow structure along the moving wall bisector is very similar to what you get in a plane channel, but at the center of the duct, the flow is more isotropic than what you have in the plane Couette flow. Now let us consider the distribution of the wall shear stress. As you can see, the distribution is not uniform. The wall shear stress is not constant at both the upper wall and the lower wall. At the bottom wall, you have 2 minimal points and 1 maximal point. Here I'm showing just half of the ducts, so Z over H varies from 0 to 1. And at the top half of the duct, you just have 1 minimal point located at the center of the duct. And if we look at the coherent structures, the high-speed streaks, can observe that the location of the high-speed streaks correspond to the minimum location in the wall shear stress. So at the bottom wall, you have 2 high-speed streaks, and at the top wall, where you have just 1 local minimum, you have 1 high-speed streak, which is centralized in the duct. Again, let us take a closer look at the coherent structures. So I'm taking a slide at different duct heights. So the top left hand figure is a slice taken at y over h equals to 1.8, and the bottom left hand figure is a slice taken at y over h equals to 0.2. As you can see, we can clearly observe the high-speed streaks formed. If you look at the figure on the right-hand side, we have a plot of the instantaneous velocity field. Again, we can clearly see the streaks. And associated with these streaks are 2 counter-rotating quasi-streamized vortices. So the vortices, the streaks are formed when the vortices transport momentum from the wall to the interior of the ducts. If you work out the frictional Reynolds number for this flow, it's about 70. So that means the duct width in wall unit is about 140. So this is barely large enough to host the coherent structures needed for a fully turbulent flow. Like I said earlier, the separating distance between these structures is about 100 wall units. That's why you can only have 2 high-speed streaks close to the bottom wall and just 1 high-speed streak close to the top wall. So to sustain a turbulent flow field, the flow has to switch between 2 states. Again, we can revisit the Reynolds shear stress, and we try to look at the contributions of various events to the Reynolds shear stress. So the Reynolds shear stress can be divided into 4 quadrants. We have Q1, Q2, Q3, and Q4. In the first quadrant, we have fast-moving fluid being carried away from the wall. So that's an ejection event. Q2 is also an ejection event where slow-moving fluid is carried away from the wall. So in Q3, you have slow-moving fluid being moved towards the wall. So that's a sweeping event. And in Q4, you have fast-moving fluid directed towards the wall. So for this quadrant analysis, we take V, the wall number velocity, to be positive when it is pointing away from the nearest moving wall. And we take our streamwise velocity U to be positive in the direction of the nearest moving wall. So if we consider the bisector of the moving wall and we plot the contributions of the various terms to the Reynolds shear stress, we obtain the plot shown on the slide. So for the top half of the duct, you can see that the Q1 event, which represents ejection of fast-moving flow from the wall dominates at the top wall, while at the bottom half of the duct, the sweeping event, which represents the movement of slow-moving fluid towards the wall, dominates. And if we consider a secondary flow pattern, we see that at the top half of the duct, where ejection event dominates, the secondary motion is convecting momentum away from the wall, while at the bottom half of the duct, where you have sweeping events, the secondary flow is carrying momentum towards the wall. So the secondary flow pattern is related to the ejection and sweeping event. So in summary, we've been able to carry out direct numerical simulation of turbulent flow in a square duct when the flow is driven by translating walls. And we found out that the critical Reynolds number for obtaining a turbulent state is about 875. This is much higher than you get in plain Couette flow. This increase in Reynolds number is in critical Reynolds number is due to the stabilization by the side walls. And for the first time, we were able to show that, like in pressure-driven flow, the turbulent flow field also alternates between two states at Reynolds numbers close to transition. And we showed that the secondary motion are induced by gradients of the anisotropic Reynolds number and Reynolds shear stresses. And then we show that the secondary flow is closely related to the near wall ejection and sweeping event. Thank you for your attention. I'll be happy to take questions.